In this chapter, we're going to be introducing logic and proofs. In this video, we're going to start looking at deductive proofs, and we're going to start by looking at number proofs. All right, hi everybody. So in this lesson here, we're going to take a look at deductive proofs. At least we're going to start taking a look at it. And we're just going to take a very kind of introductory look at proofs. We're not going to go terribly deep into it. We're not going to get really technical. We just want to get the idea of a proof across to you. So, like it says up here, the idea of a proof in mathematics is really important because you can only work with confidence with concepts that have been proven. And a mathematical proof is an argument, and it can take on several forms. These things can have all sorts of different ways of structuring them and arriving at the conclusion here. But the whole idea is that in every case here, it unambiguously establishes the truth of a statement, of a mathematical statement here. Okay. So now, okay, why is this so important? So first of all, proofs can help you determine whether or not a statement or a result is true or false. Okay, and sometimes, and it's the issue here is really this last statement here. Sometimes it's not intuitive. Sometimes the results that you're looking at here are not intuitive, and so the proof helps establish that relationship and to convince you if something is true here. Proofs are also excellent for laying out clearly the relationships that exist between what sometimes seem to be unrelated ideas. Okay, so they can help you understand how ideas are connected or related. Okay, and there's some wonderful examples of that in mathematics where as you work through the proof of something, you can see how two ideas that you would never have connected before, all of a sudden, you need an idea to show that something else is true. It's been really cool. Proofs are used by mathematicians to communicate with each other. So most proofs, and I heard this once from a professor, and I don't know if this was like his main thesis here, but he kind of just said it, and then he glanced by and kept going here, but it really stuck with me here. Most proofs require two steps. The first is you convince yourself that you understand a concept, and then the second is to convince someone else. And if you can't convince somebody else that you understand it, then you haven't really proven it. Okay, so it's about communication, communicating ideas. Proofs force people to order their thinking. You got to be structured about it because sometimes, like it says here, sometimes ideas come quickly and in a haphazard way, and we just need to organize our thoughts, and a proof will help force you to do that. And kind of finally here, well, proofs often lead to, hey, new mathematics. Okay, that happens a lot, new mathematics, and that's always exciting. So first of all, some tips to writing proofs here is be explicit at the beginning of the proof about what it is you're proving, and then at the end when you've reached your conclusion. Okay, so we want to have a really clear beginning and a really clear end, and we're going to help you with that. You might find it necessary to use examples to guide your thinking, and that's fine, but remember that examples are not sufficient to prove something, okay, unless you've got an exhaustive collection of those examples. We had talked about that in a previous lesson about inductive reasoning, where you go from examples and you just generalize from those examples. Well, that's not enough. Okay, so if we ask you to prove something and you just give a couple of examples, that doesn't prove anything. You typically, now this is in a proof, like a school proof here, you typically should use all the hypotheses that you're provided here. Basically, when we give you some information and ask you to prove something, you probably should use all the information that we're providing you. It's all probably significant in some way or another. For identity proofs, okay, so for identity proofs here, you are trying to demonstrate that the left side of an equation is in fact equal to the right side of the equation, and here it is, without making use of the implied equality. In other words, without going back and forth, moving stuff back and forth across the equal sign here. When you're working with an identity proof, basically you're trying to prove the equality, so you can't assume the equality. There's a lot of things that we do, okay, with an equation because we assume that equal sign is true, that the left side is equal to the right side, and that allows us to do certain things. But if you're questioning the equality, then you can't do that. So you have to make sure that the left side and the right side both independently equal the same thing. And then you should end that by saying that the left side is equal to the right side. Okay, we get our students here, we get our students to basically end that with LS is equal to RS. Left side is equal to right side. And then we got here, for a number of proofs here, or for number proofs and equivalence proofs, I should say, it's customary to end with QED. Okay, so that's Latin. Okay, you got the Latin there, quod errata demonstrandum, which is what was to be shown. Basically, we take that to mean that thus it has been demonstrated. So end of my proof, I give this little QED to tell everybody that I'm done. I've finished. Okay, now that's customary. Sometimes you'll see people actually use a little bit of different notation there. I've seen in some places here where what they'll do is they'll use a little square at the end to indicate that the proof is over. Okay, it doesn't really matter, but we just need something to indicate that the proof is done, that I've demonstrated, or in my mind, I have demonstrated what it is I tried to demonstrate here. And just know, everybody, that it takes practice. It takes practice to get good at doing and writing proofs here. Now, our goal over the next few lessons here is not to really give you like a way of coming up with proofs that would be like publishing quality, right? We're just introducing this idea and kind of giving you a push forward here. So there are going to be some little inconsistencies here and there along the way here, but it's really just so that we kind of get you used to the idea, and then later on we're hoping that somebody will build on that. Okay, so now we're going to take a look at our first section here called number proofs. Okay, so in number proofs, and we're going to do some number proofs in here in a bit, but just to kind of talk about where this is kind of heading here. So we know that calculations play a huge role in many proofs. Okay, I mean, granted, these are mathematical proofs. You would expect some calculation in there, and the reasoning is typically quite easy to follow when it comes to those kind of calculations, because when we solve those kinds of expressions or equations, we are applying the reasoning by equivalence. Okay, talking about what happens with that equal sign and what that equal sign does for us. So each step along the way requires deduction, but it is a stronger process here because the type of reasoning, in this type of reasoning, the converse must also be true for each of our implications. In other words, we've got this forward and backward sort of thing. The rules that we apply can be done and undone. I can multiply, or I can divide and undo that multiplication. I can add or subtract to undo that. And that allows us to kind of move really quite confidently through some of these proofs. And in a lot of cases, because you're already really familiar with those steps here. Now, these kind of proofs here, or equation solving, I should say, because that's ultimately what we're doing, when we apply that kind of reasoning, that is really based on the assumption here that two equations are equivalent if they have the same solutions, and two functions are equivalent, okay, if f of x and g of x are equal for all values of x. Okay, now, granted, so even if it's undefined, it'll be undefined on one side or the other here, right? So somebody might say, well, what if that's not defined someplace? Well, in both cases, it would be undefined there. But that's sort of what we do when we're talking about reasoning by equivalence. And we're going to get to that in just a little bit, okay? For right now, what we're going to do is we're going to kind of back off that a little bit, and you're still going to see a little bit of the calculation aspect of this come in. But that's kind of what we're going to just focus on. It's just some really basic calculations here and some assumptions that we have, and we're going to prove some things here. So I just want to walk you through a couple of examples here. And then in another lesson, we'll really get into these equivalence proofs here. But for right now, let's just take a quick look at a couple of examples, and then we'll do a few more together here. So first of all, we're going to prove that the sum of three consecutive integers must be a multiple of 3. Okay, so that's what we're going to work with here. So notice that what we're starting with here is we're starting with 3 consecutive integers that we're going to add together. We're going to sum them up. So what I need is kind of a general way of diving into this. So I am going to let a be that first integer. Okay. And then my next 2 consecutive numbers here are going to be a plus 1 and then a plus 2 would be the next one. And I hope that makes sense. When I add 1 to an integer, I get the next integer. And I add 2, I get the integer that's 2 down. If we then add those up, we're going to take a, the first one, plus the second, plus the third. Okay, and we're already quite comfortable with these operations of addition, right? Like this, I don't think it's any big surprise here that I can drop those parentheses quite easily and that I get 3 a's, 1, 2, 3. And then if I add the 1 and the 2 together, I get 3 at the end there. So I get 3a plus 3. Now, remember what the proof was asking us to do. We wanted to show that the result was a multiple of 3. So it suffices for me to show that you can factor that result, okay? And it's going to become 3 multiplied by some integer value. And so as a result, I know that the final result is a multiple of 3. So like it says here, since 3 is a factor of the sum, and since a plus 1 is an integer, if a is an integer, so basically that's the fancy way of talking about that is integers, okay, are closed under addition. Oops, was right. Under addition. In other words, when we add integers together, we get integers. Okay, and that's something that we kind of assume to be true about integers, and that's fine. Then the sum of 3 consecutive integers is a multiple of 3. And we're done. Okay, what we wanted to prove, we've proven. Now, it helps, okay, in a more general sense here, it helps to have a little bit of notation that we can generalize about even and odd numbers. So, for example, if we start off with just allowing n to be a natural number, and it doesn't actually have to be a natural number here. We're using that because of a couple of the resources that we have been we will be using with students here uses the natural numbers there. So we're just being consistent with that. So if we just let n be a natural number, we know that 2n is going to be an even number. It's going to be a number that's divisible by 2. And just like if that's true and we let n be a natural number, 2n plus 1 will be an odd number. So we're going to use these two kind of structures here to help us deal with proofs about odd numbers and even numbers. And then a rational number is in the form p over q, where p and q are both integers, and we add that extra little bit here. Then we don't want q to be equal to 0 because that would make these things undefined. We don't want that. So let's take a quick look at a proof here that's been laid out for us, and then we're going to start to do a few together on our own here. So prove that the sum of two odd numbers is even. So we're going to let, first of all, here's how we do this. And actually, probably should drop that down a little bit lower. We're going to let m and n just be our positive integers here. Now, positive integers here probably could have been the same here as the n. In fact, I'm almost tempted to come up here and just say, you know what, this really could just be the integers here. Oops, could be the integers, and that it works both ways there. We're going to let m and n be positive integers, and then the expressions 2m plus 1 and 2n plus 1 will both be odd integers, okay? So we've got two different, and the reason why we're using m and n here is so that we get two different odd integers, okay? Then their sum is going to be 2m plus 1 plus 2n plus 1 is going to equal 2m plus 2n plus 2. Now, notice that expression here, we can factor out a 2. So 2 is a factor of the result. And there it is. So since 2 is a factor of the sum, and we know that, just like we said before, the integers are closed under addition. If we add these three together, we're going to get another integer. Then we know that our final result is going to be an even number. So therefore, the sum of two odd numbers is even. And that's the end of our proof, QED. So I hope that gives you a little bit of a sense of how that works. Now let's take a look at just a handful that we will work on together here. They're not all going to be about odds and evens and numbers like that, but hopefully there'll be ideas that you're kind of familiar with, and you'll get comfortable with how we walk through those proofs by just seeing a few examples. Okay, here we go. So first question is prove that the product of two odd numbers is odd. Okay, so we're going to, whoops, I keep doing that. We're going to let m and n be elements of the integers. Okay, we're going to stick with integers here. So 2m plus 1 and 2n plus 1 will be two different odd numbers. Now, I want to do it like that because I don't want to use like 2m plus 1 and 2m plus 1 because that's just the same odd number twice here. And there might be some special relationship when you, for example, square an odd number that produces an even number, right? Like I know that's not true, but I'm just saying that you don't want to have sort of like kind of an assumption work its way through your work unintentionally. So 2m plus 1 and 2m plus n plus 1 means we've got two different odd numbers here. Now let's multiply them together. Okay, so we're going to get 2m plus 1 multiplied by 2n plus 1, and that is going to equal, we're just going to do some distribution here. So 4mn plus 2m when I multiply the 2m through, and then 2n plus 1. Now notice that out of the first three terms, I can factor out a common 2. That leaves me with 2mn plus m plus n and plus 1 here. Now, I am going to let 2mn plus m plus n equal, let's say, t. Okay? And I know because the integers are closed under multiplication and addition, because when I multiply 2 by m by n, and if those are integers, I'm going to get an integer. And if I add the integers together, I'm going to get an integer. I know t is an integer. So therefore, okay, the result, okay, 2t plus 1 is an odd integer. Therefore, I can go one step further and say the product of two odds, whoops, is odd. Now let's take a look at this next one. It says, prove that for all positive integer values n, the expression n squared plus 7n plus 6 is composite. Okay, now what you might notice right off the bat here is that n squared plus 7n plus 6 is going to be an integer, okay? Because integers are, like we said before, closed under multiplication and addition here. So squaring that integer, multiplying by 7, and then adding those up, we're still going to get an integer value there. So to start off with, we're going to let n be an element of the positive integers, and we typically write it like that. Okay, our little symbol for the integers plus a superscript positive sign. Now, notice that n squared plus 7n plus 6. And in a little bit here in another lesson, we're going to talk a little bit more about how this works here. But notice that I can factor this. And by this time here, you've probably had a fair bit of experience factoring. And you'll see that this is going to be n plus 6 multiplied by n plus 1. Okay, and again, remembering that the integers are closed, we know, therefore, that n plus 6 is an integer. And n plus 1 is an integer. And so as a result, what we can do here is the expression, okay, therefore, n squared plus 7n plus 6 can be factored into the product. Okay, and I'm going to run into the end here, so just let me move this up a little bit. Of two integers, so it is composite. Because that's what a composite number is by definition. And that's all we really needed to show. Okay, let's take a look at another one here. So now for this next question, Okay, it says we're going to prove that 0.9 repeating is an element of the integers. Okay. So, and I suspect there's probably a bunch of different ways to do this, but the first way that kind of occurred to me is I was going to convert this into a rational and just take a look at the rational expression of this. And so typically what we do with that is I'm going to let 0.9 repeating, I'm going to let that be equal to n. Now, remember what that means here. So that means that this is going to be 0.999 kind of repeating on and on forever. And I'm going to let that be equal to n here. Now, what I'll do here is I'm going to multiply both sides by 10. And if I do that, I get, okay, 9.9 repeating, and then 10n on the right-hand side. Then I'm going to subtract from that, I'm going to subtract n. Okay, and remember, n originally was this expression right here. So when I subtract that from both sides, I'm going to subtract 0.99 repeating. And that's going to be to subtract n here. And when I do that, on the left-hand side, something kind of nice happens there. That just becomes 9. And on the right-hand side, that becomes 9n. And now when I solve for n, I get 1 here. Now remember, n was initially 0.9 repeating. And now I've been able to show that n is actually equal to 1. So since n is clearly an element of the integers here, it's equal to 1. So that makes it an integer here. We know that 0.9 repeating is an element of the integers as well. I mean, because it's the same thing. They are the same variable there. There's just another way of writing it. And there we go. Again, probably not the best proof in the world, but it gives you a sense of how that all kind of hangs together there. And then we're going to take a look at this one here. Prove that the difference between any two rational numbers is also a rational number. Okay. So to create rational numbers here, what I'm going to do is I'm going to let A, B, C, and D all be elements of the integers. Okay. And we're going to be really specific here, where C isn't 0 and D isn't 0. We're not going to let those two go to 0 here. And you can probably guess even at this point right now that that's because I'm going to make those the denominators. So we're going to get A over C, and we're going to prove that the difference between any two rationals, A over C minus B over D is what we're going to look at here. And we're going to show that that is also a rational number. And now remember how we're going to do that. Do you think back to how you deal with fractions, right? We're going to find a common denominator, which means I'm going to multiply numerator and denominator on the one side by the same thing. So I'm going to multiply, in this case here, numerator denominator by D, and here I'm going to multiply numerator denominator by C. So from there, I will get AD over CD minus BC over CD. And then because the denominators are the same, okay, I can actually write those over the same same denominator. So AD minus BC over CD. Okay, I'm allowed to do that. It's basically like factoring out that common division by CD. Okay, so in other words, I could have maybe looked at it like this. I could have maybe looked at this as 1 over CD multiplied by AD minus BC. The only reason I bring that up here is because I know that sometimes when you're talking about division, that's not always clear to people that you can do that, and yet you can. Yeah, you can. So since the integers are closed, closed under multiplication, okay, and subtraction. I know we've talked about that a little bit before here. We know that AD minus BC is going to be an element of the integers. Okay, and likewise, CD is an element of the integers. And additionally, because of the restrictions that we have up here that neither C or D is going to be equal to 0, we know that CD is also not equal to 0. And so therefore, the result is rational. Okay, it's going to end up being an integer over an integer. And there we go. That's what we wanted to show. Okay, and once again, these are not really great, slick proofs. kind of rough and tumble proofs here, but that's okay. We just wanted to get the sense of how proofs go, what you might do, particularly in this case here, how you might work with some numbers, give you a sense of how that works. And then we'll move on to look at some other forms here before we kind of leave this whole idea behind.